We know that in photoelectric effect and Compton scattering, the photon interacts with orbital electrons. In photoelectric interaction, the incident photon interacts with a tightly bound inner shell electron. In Compton interaction, the incident photon interacts with a loosely bound outer shell electron. And we just learned in our previous video that in pair production interaction, an incident high energy photon interacts with the electromagnetic field just outside the nucleus. Now here is a question. What happens when we push the energy of this photon even higher? In photodisintegration, the high energy photon completely bypasses all outer defenses. It crashes directly into the actual nucleus of the atom. Let us dive deep into photodisintegration as our fifth and last type of photon interaction with matter. During this violent hit, the nucleus absorbs 100% of the photon's massive energy. This incredible burst of energy completely destabilizes the nucleus. It directly pierces the strong nuclear binding energy holding the core together. To relieve this massive instability, the shattered nucleus must react. It violently ejects a subatomic particle directly from its core. It can sometimes eject a proton, but it most commonly ejects a heavy neutron. Breaking apart an atomic nucleus requires massive energy. Therefore, this interaction operates under a very strict energy threshold. It physically cannot happen below a certain limit. The absolute minimum energy required is 7 to 10 mega electron volts. The probability of this interaction actually peaks around 15 mega electron volt, and the probability strictly increases with the atomic number of the target material. Why is this absolutely important for your daily clinical practice? Think about using extreme high energy treatment beams. You might use 15 or 18 megavolts in your clinic. Some photons in such high energy beams easily exceed the 10 MeV threshold. These extreme photons strike the heavy metal components inside the linear accelerator head. When they strike these heavy metal components, they trigger this exact nuclear reaction. This ejects a deadly stream of fast flying neutrons into your treatment room. This creates severe neutron contamination. We call it neutron contamination. Listen carefully now. Neutrons are incredibly dangerous to humans. They are almost 10 times more effective at causing lethal damage to human DNA than your standard X-rays. This specific interaction becomes a massive occupational hazard. This physics dictates exactly how we build our radiotherapy bunker. This is why your radiotherapy bunkers require extensive shielding. You must use highly specialized hydrogen-rich shielding. Materials like polyethylene or specialized concrete are used to successfully slow down and absorb these deadly neutrons. Let us understand the sequence of this interaction again. This is how this type of interaction looks like. We can call it a violent 100% energy transfer. The incoming extremely high energy photon approaches the heavy target nucleus. See here. This photon crashes directly into the atomic core. During this exact moment, it transfers absolutely all of its massive energy directly inside the nucleus. It deposits 100% of its energy right into the core. This incredible sudden burst of energy completely destabilizes the target nucleus. It totally disrupts the delicate balance of the atomic core. It successfully penetrates the strong nuclear binding energy that holds the entire atom together. The nucleus simply cannot contain this massive amount of extra energy. It becomes violently unstable and must immediately react to survive. To survive, the nucleus must immediately and instantly relieve this intense pressure. The shattered nucleus must expel a subatomic particle directly from its core. At extreme energies, it is physically possible for the nucleus to eject a proton. It can sometimes even eject multiple nucleons. But in most scenarios, it ejects a heavy neutron. This specific free-flying neutron is exactly what creates a massive safety hazard inside your linear accelerator bunker. Let us now look at a strict energy rule that control photodisintegration interaction. See, breaking apart an actual atomic nucleus is very difficult. It requires a massive amount of energy. Look at this graph. Because it takes so much energy to break the atomic core, this reaction operates under a very strict energy threshold. The interaction cannot happen below a certain limit. As you can see, the absolute minimum threshold is between 7 and 10 mega electron volts. If your incident photon has less energy than this, the nucleus remains completely safe. But once we cross this threshold, the probability rises rapidly. Look at the orange peak in the center of the graph. The maximum probability for photodisintegration occurs right around 15 mega electron volts. Now we should also remember the target rule. The probability of photodisintegration interaction increases with the atomic number of the absorbing material. This specific combination of extreme energy and heavy atomic numbers is exactly what creates massive safety hazards inside your linear accelerator bunker. Why should we radiation oncologists care about this interaction? See, we frequently use standard high energy beams in our daily practice. We sometimes treat deep-seated tumors with 15 or 18 megavolt beam. Now you might be thinking, what is a big deal if I use 15 megavolt beam? Listen, when you set your linear accelerator to 15 megavolts, you are actually setting the maximum or peak energy of that beam as 15 megavolt. Because clinical X-ray beams are polyenergetic, they do not contain photons of just one single energy of 15 megavolt. Instead, they consist of a wide spectrum of different photon energies ranging from very low energies all the way up to that 15 MeV peak. Remember a standard rule of thumb in medical physics. The average energy of a polyenergetic X-ray beam is approximately 1/3 of its peak energy. Therefore, if you have a 15 MeV beam, you simply divide that peak by 3, which means the average photon energy is roughly 5 mega electron volts. We just saw that the threshold for photodisintegration is strictly 10 mega electron volts. So why is there a problem if our average is only 5 mega electron volt? The answer lies in how our linear accelerators actually work. Because even the average is only 5 MeV, the beam still contains a significant number of high energy photons that reach up to 15 MeV. These specific high energy photons easily cross the 7 to 10 MeV threshold needed to trigger photodisintegration, which is exactly why neutron contamination still occurs. These specific ultra high energy photons are the ones that create a massive safety hazard inside your clinic. Where exactly this dangerous interaction actually happens in your department? See, when you use these ultra high energy beams, the photons must pass through the gantry head of your linear accelerator. Inside that gantry head, we have very heavy metal components like the target and the collimating jaws. Please remember, these components are made up of heavy elements with a very high atomic number. So, what happens when a powerful 15 megavolt photon crashes into these heavy metals? It triggers photodisintegration. Photodisintegration interaction happens. This violent nuclear reaction instantly produces an extremely dangerous stream of free-flying neutrons. As I said earlier, we clinically call this massive hazard neutron contamination. And this is not just happening inside the machine. If the patient has heavy elements or metallic implants inside their body, this exact same reaction can happen right in the tissue. These free flying neutrons are highly lethal and they flood your entire treatment room. We just established that photodisintegration creates a massive stream of fast neutrons. But why are these specific particles so incredibly dangerous to us? See, neutrons themselves are completely uncharged particles. However, when they interact with human tissue, they produce secondary recoil protons. Look at the DNA diagram on your slide. These recoil protons create heavily damaging tracks of dense ionization right through our cells. This severe concentrated damage completely destroys the human DNA. Because of this extreme destruction, neutrons result in a massively high relative biological effectiveness or RBE. In fact, they are almost 10 times more effective at causing lethal DNA damage compared to our standard X-rays. Yes, 10 times more effective. This is exactly why even a small amount of neutron contamination creates a big threat to your occupational safety. This slide shows a very sobering clinical reality. See, we must always weigh the risk and the benefits for our patients. When we use these extreme energies, we expose the patient's entire body to these dangerous neutrons. This unwanted whole body neutron exposure provides absolutely zero therapeutic benefit to your actual target volume. It does not help cure the tumor at all. Not only this neutron exposure acts as a major contributory factor for second malignancies. These second malignancies cancers can appear many years after the primary cancer is successfully cured. This is a completely unacceptable risk for our patients. And this brings us to a very strict rule in our daily practice. This is the absolute primary reason why we rarely ever exceed 15 or 18 megavolts. The subatomic physics simply makes the long-term risk far too high. The risk-reward ratio is totally not in favor. There is a major problem when we design our treatment bunkers. See, we are naturally trained to rely on heavy lead for radiation protection. We routinely use thick lead to successfully stop standard X-rays and Compton scatter. Lead works perfectly for X-rays because it relies on a massive electron density to attenuate the beam. But shielding against fast neutrons is completely different. Listen very carefully. Heavy lead is absolutely terrible at stopping fast neutrons. Why is that? See, neutrons are completely uncharged particles. They do not care at all about the dense cloud of electrons inside the lead. They simply fly right past those electrons without interacting. Because they ignore electron density, materials like solid lead becomes almost entirely useless against these neutrons. So, if our standard heavy metal fail, what should we actually use to stop them? See, to stop a fast flying neutron, you need its exact physical match. Look at the top diagram. If you fire a fast neutron at a massive heavy lead nucleus, it is like throwing a small billiard ball at a very big bowling ball. It just bounces off and keeps flying with almost all of its original dangerous speed. Now look here. This shows a neutron crashing directly into a hydrogen nucleus. A hydrogen nucleus is basically just a single proton. The physical size and mass of a flying neutron is almost exactly identical to this hydrogen nucleus. This is exactly like a fast moving billiard ball crashing into a similar resting billiard ball. Because they share this strict mass equivalence, The flying neutron transfers almost all of its kinetic energy during the crash. This perfect physical match is exactly what successfully steals the neutron's energy and slows it right down. We just saw how hydrogen is the perfect physical match for a fast neutron. Now look at the exact sequence. When these highly dangerous fast flying neutrons crash into these identical sized hydrogen nuclei, they undergo what we call a perfect elastic collision. See, because the neutron and the hydrogen nucleus are the exact same size, the fast neutron instantly transfers almost all of its kinetic energy to the resting hydrogen. This collision causes a massive and sudden drop in the neutron's speed. This rapid slowdown completely neutralizes the immediate threat. It instantly converts these deadly fast particles into slow, weak thermal neutrons. And this specific conversion is exactly what we must achieve. So, once they are successfully slowed down to this weak thermal state, they can finally be easily captured and safely absorbed by our treatment shielding. We just saw how hydrogen stops the fast neutron. So how do we actually build this into our clinic? Look at the diagram of the linear accelerator bunker. See, standard concrete and heavy lead are simply not enough. Your high energy mazes need something extra. Your heavy vault doors need something extra. They must be packed with thick layers of hydrogen-rich materials. Look at the blue sections in the diagram. These blue section shows the polyethylene. Materials like solid polyethylene are used for this exact purpose. Remember the billiard ball collision we just discussed. The massive amount of hydrogen in polyethylene forces the fast neutron to crash. This rapidly slows them down. They become weak thermal neutrons. Once they are slow, they are easily captured. They are safely absorbed by the shielding. This specific engineering stops the deadly neutron swarm. It stops them before they can ever reach your control area. It brings us to a very serious conclusion. See, understanding the exact mechanism of this photonuclear reaction is absolutely non-negotiable. We must deeply master this physics to guarantee absolute safety in our clinic. This specific knowledge directly dictates our daily beam selection. It dictates exactly how we engineer our high energy clinical wards. And most importantly, it dictates the long-term survival of both our patients and our occupational staff. This is exactly why we must never take our linear accelerator shielding for granted. Thanks for watching. See you in next video. Signing off, Parveen Ahlawat.